So today we are going to be learning about how to graph, sine, well, actually all periodic functions.
Aw, dang it.
And hopefully, if we have time, we're going to learn about modeling periodic behavior, but one thing at a time. So the generalized sine function looks like this. What do I want to use for? Do minus there. Okay. So each one of these variables, I know this looks complicated, but each one of these variables here, well, they're not actually variables, they're constants.
What's the difference?
If I actually wrote out an equation, like a specific equation, these would all just be numbers.
Okay.
Yeah. Okay. And they each do different things. So A, have you ever done any kind of function transformation? Like how they change whenever you add? No? Okay. So A here, it's being multiplied by the entire function, or the sine function. What this does is it stretches or shrinks the sine function. Or actually, we'll just say the function, because the cosine is going to look very similar. B, and this, sorry, excuse me, this is vertically. So it's going to make it tall and skinny or short and fat. B stretches or shrinks horizontally. Exactly. Good. Because it's also being multiplied. It's multiplying by the inside, which, by the way, the inside of a function is what we call the argument. And this is actually true for any kind of function, but yeah. So it stretches or shrinks horizontally because it's multiplying by the argument. This thing right here, I'm not going to make it complicated. I'll call it C. C is what we call a horizontal translation or shift, which just means that it moves it to the left or right. And if it's minus, it moves it right.
Isn't that true for like all
Mm-hmm. Yeah, so you have done this before.
I bet with polynomials?
Yeah, it's the same idea, the exact same idea. And if it's plus, it shifts it left. Okay, and then what does K do?
Moves it vertical translation?
Yeah, vertical translation. And if it's positive, which way does it go?
Up,
Up, right. And if it's negative?
down.
I guess there's only two options. Now, we do need to actually do the same thing for the stretches and shrinks. So it stretches if, for B, it's weird. It stretches if it's between 0 and 1. In other words, if it's a fraction, like 1/2, 1/3, etc. And it shrinks if it's greater than 1. Yeah. A works the exact opposite way. So A stretches if it's greater than 1, and it shrinks if it's a fraction.
Why is that?
That's a good question. I do not know the answer to it. I would just say that's kind of just how it works. What happens on the inside of the argument is kind of the opposite of what happens outside. So on the outside, whenever k is positive, it shifts it up. When a is greater than 1, it stretches it, and on the inside, it's kind of the opposite. When it's negative, it goes in the positive x direction, the right, to the right. And b stretches it whenever it's a fraction. And then the only other things are flips. If A or B are negative, or reflections is the proper term for it. Well, if A is negative, it's a vertical reflection. And if B is negative, what do you think?
It's a horizontal.
Mm-hmm. Exactly. Okay. So we have all these possible transformations, but we don't even know what the dang function looks like, so we should probably do that. Should probably just show what the actual function.
Is it where it goes like up and down?
It is. It is. So, yeah, the basic function looks like this. And hopefully your knowledge of the unit circle will come in handy here. So let's start out with the sine function. Remember, the sine function, the value of it is the y coordinate on the unit circle. The y coordinate. So at 0 degrees, what is the y coordinate? Or what's the point, first of all, at 0?
0?
Mm-hmm.
0.
No, like the coordinate point. You know what I mean?
0, 0?
That would be at the origin. Remember, it's out by the radius. On the unit circle? Okay, let's look. Where is our unit circle? So here's our unit circle. Our point is 1, 0. Okay? Oh, you know what? You did say this. I'm sorry. It's 0. You're right. The y coordinate is 0. So at theta equals 0, the angle,
Mhm.
sine is 0. The y-coordinate is 0. Okay. And then what about at pi over 2? Let's actually just write these. We'll go pi over 2, pi, 3 pi over 2, 2 pi. So what is it at pi over 2, or 90 degrees? The y-coordinate.
1.
1, right, good. It's 1. At pi, 180?
0.
0, good. 3 pi over 2, which is, what angle is that in degrees?
Negative 1.
Negative 1, yes. What angle is that in degrees?
270.
Good, 270. And then at 2 pi, well, that's just the same as 0.
0.
So it's 0. Right. So the function looks like this.
What's this function?
This is the sine function. And we could go in here and plot all the points out. If you did,
It's just going to go like that.
it's going to go like that forever. It's what we call a periodic function.
I've seen that before when I was just messing around with Desmos one day.
Mm-hmm.
I didn't understand what it was talking about, but I remember seeing that.
Well, now you know. Yeah. Okay. Okay, and then let's think about the negatives. So we haven't really discussed this yet, but another way of thinking about negative angles is just, let me write these out first. Negative, negative, negative 2 pi. Is just going around the unit circle backwards. So negative pi over 2, we would just go this way instead of this way. We'd go around clockwise. So negative pi over 2, negative 90 degrees, is the same as 270.
Mm-hmm.
So our y-coordinate there is negative 1. What about for pi? Or negative pi, excuse me. That would be the same
0.
as what? Yeah, it's the same as pi. What about negative 3 pi over 2?
1.
1, right?
0.
And 0, yeah. So notice that on either side of the y-axis here, the function is anti-symmetric. In other words,
It's just the same thing flipped.
it's the same thing flipped, right? So if you go over pi over 2, it's the same thing as negative pi over 2. So this brings us to like a rule that you will use pretty often. It has to do with something called parity, but basically what it says is that sine of theta is equal, sine of negative theta is equal to negative sine of theta, which is what we said. So if we plug in a negative angle, it's equal to the negative function value of the positive angle. Negative 1 at negative pi over 2. Negative that. Negative negative 1 is positive, so that's equal to what it's at pi over 2. I said that very weirdly. I'm sorry. But yeah, so that's the basic sine function. Okay. And so let's say we did a transformation on it. Let's say we did f of x is equal to 2 sine of theta minus pi over 4. Let's do pi over 2. Plus 1. So first of all, what are all the transformations? This is our original function here.
I don't know.
Well, let's look at the list of them. So again, A stretches or shrinks the function. B stretches or shrinks it horizontally. C translates it left or right. K translates it up or down. So which of those do we have? A, B, C, or K?
A, C, K.
A, C, and K. Good, good. Okay, so what are they going to do to it? What's 2 going to do?
Make it shrink.
So it's greater than 1, right? Which means it's going to stretch it. It's the opposite as B. So it'll stretch it vertically. Okay. What about, you said C. What's C going to do? Or pi over 2 in our case.
Move it right.
Move it right, yeah. So, K. And then K is what?
Gonna move it up.
Move it up. What is our K here?
1.
1, right. Okay. So we can do that. Let's fill out a little table of values first, though. So if we have our theta, and I keep writing f of x, I need to write f of theta. We don't have an x here. Okay. So let's do 0, same degree. Pi over 2, pi, 2 pi. And we might fill in between there. So let's plug in 0. We have 2 sine of 0 minus pi over 2 plus 1. So that gives us 2 sine of negative pi over 2 plus 1. So what is sine of negative pi over 2? That would be the y-coordinate at negative 90. So let's break that down. So negative 90 is the same angle as what?
270.
270, okay. Sine means the y-coordinate at 270, which is what?
Negative 1.
-1, good, okay. So sine of negative pi over 2 is just -1. Okay, so that's 2 times -1 plus 1, that -1, good. Okay, now sine of, or this pi over 2, so 2 sine pi over 2 minus pi over 2 plus 1. Well, sine of pi over 2 minus pi over 2, that's just sine of 0. What's sine of 0?
0.
0, yeah, good. So that's just 0 plus 1, so it's just 1. Okay. What is, let's see, 2 sine pi minus pi over 2 plus 1?
2 pi over
2, wait, what?
2. What?
Pi minus pi over 2, that'll give us just pi over 2. Positive. What's sine of pi over 2?
Pi over 4.
So what comes out of a sine function, the result of a sine function is going to be just a number. There's not going to be a pi in it usually. So sine of pi over 2, that's the y coordinate of pi over 2. What's that? 1. Good, yeah. So that's 2 times 1 plus 1, which is
2.
2 plus 1.
3.
3, yeah. Okay, and then 3 pi over 2. We have 2 sine 3 pi over 2 minus pi over 2 plus 1. So what's 3 pi over 2 minus pi over 2?
2 pi over 2.
2 pi over 2, which is just
1. Negative
1 pi. The 2's will cancel, right? So it's just pi. Okay, so
So
yeah.
it'd be 0.
Yeah. Yeah, sine of pi is 0. So, well, that's 0, but we still have the plus 1. So it'll be 1. Okay. And finally, 2 sine 2 pi minus pi over 2 plus 1. So now this
3 pi over 2.
3 pi over 2, right? Which is sine of 3 pi over 2 is what? The y coordinate of 3 pi over 2.
1. It's either 1 or negative 1.
Well, what's 3 pi over 2? What's that the same angle as?
270.
270.
So it's negative.
So it's negative 1. So 2 times negative 1 plus 1 is equal to, well, negative 1. Okay, so we got our points now. We have negative 1, 3, 1, negative 1. Let's plot that out. Negative 1, then 3, one, I feel like we did something wrong here. Negative 1. Oh no, positive. Negative 1, 3, 1, negative 1. We did something wrong here. Hang on.
You did?
I think so. So let's see. We have 2. You know what? Let's go to Desmos and plot this. Let's see.
You go on Reddit.
On Reddit? Yeah.
I mean, there's probably some obscure page where you could probably find math problems like this.
Oh, I'm sure.
I would have put it past the people who had read it.
Okay. So let's do, well, okay, so at 0, we had -1. Is that what we had? Yes. At 0, we had -1. Why is it not? Okay. At pi over 2, we had 1. Oh, no, we did it right. We did it right. I just missed a point. Excuse me. So at pi over 2, we had 1. At pi, we had 3. At 3 pi over 2, we had 1. And at 2 pi, we had -1. -1, 3, 1, -1. Yeah, okay. So basically, what's happened here is if we keep on graphing this, it's going to look like this, kind of. It's very poor, but what we've done here is we've shifted right. Mm-hmm. We've shifted up, which means our new 0 point is 1, kind of. So we've shifted up and right, and we've stretched it, which is exactly what we said we were going to do. Okay. So this is kind of what you're going to be doing on your homework. I'm not going to give you too many problems because I want you to do this. I want you to plot the points or find the values for each of the points. So I'll probably give you like 3 or 4 problems, okay, maybe, and that way it's not too many that you can actually do this, mm-hmm, and it doesn't become overwhelming. But yeah, you're going to be doing that very, very similar stuff. I'm not going to be able to get to the other thing today, but it's all good. We're going to do some more of this because I want you to feel comfortable with it before you do your homework. Okay. How did you feel about that, by the way?
I feel pretty good about it.
Okay. So the other one that we're going to do, we're not going to worry about tangent or the reciprocal functions right now. We're just going to do sine and cosine. Oops, spilled coffee. The other one is cosine. Oh, and so the general function for cosine is A cosine B theta minus C plus K. So it's almost the exact same thing. The only difference is that it's cosine instead of sine, right? Mm-hmm. All right. Now, the base function for cosine, I'm not going to go through all the transformations again because they're the exact same. I'm going to make this wider this time. Now, on your homework, by the way, you can use Desmos to check yourself. But like I said, I do want to see a table of values there. But one thing Desmos might be helpful with is I picked going up every pi over 2. So I started at 0, pi over 2, pi, 3 pi over 2, etc. That might not always be useful. And in fact, I think we'll see a case here where it's not. Because sometimes if you stretch it horizontally or shrink it horizontally, you're not going to get very much information by just going every pi over 2. You might have to go every pi over 4, something like that. Okay, so let's plot this one. What is the, now sine functions, they are the y-coordinate on the unit circle.
So this one goes up and down?
This one still goes up and down. They're both very similar looking functions, you'll see. But the cosine function is the x-coordinate. Sine function was the y, cosine function is the x. So what's the x-coordinate of 0 degrees?
1.
1, right. So at sine of 0, or at theta equals 0, cosine is 1. So this is just the basic cosine of theta function. Okay. What is sine or cosine? Oh my gosh, I can't speak today. What is the x-coordinate at pi over 2 at 90 degrees?
0.
0. Good. And at pi?
-1.
-1. And at 3 pi over 2?
0.
0. Are you sensing a pattern? And at 2 pi? 1. And we could keep going on and on. Okay. Now, what's the x-coordinate at negative pi over 2?
0.
Good. 0. Negative pi?
1.
Well, negative pi is the same thing as pi,
Negative
right?
1.
Negative 1, right? Yeah. Negative 3 pi over 2, which is the same
0.
thing as pi over 2, yeah. And then 1. Okay. So if we plot this out, it will look like this. Kind of like that. So, and if we keep going, it just keeps doing the exact same thing. So notice, if we took these two plots and looked at them, this one, this sine, the green function up here, starts at 0, 0. It kind of looks like we just shifted this function to the left. And we moved that 0, 0 point to here, negative pi over 2, 0. But other than that, if we shift it to the left by that, they're the exact same function. And in fact, that's an important identity that we'll come up with in a little bit, which is that cosine of theta is the same thing as sine of theta minus pi over 2. No, I wrote that wrong. Anyways, also though, another thing to notice is that if we go to pi over 2 here, it's equal to 0. If we go to negative pi over 2, it's equal to 0. If we go to pi, it's equal to negative 1. If we go to negative pi, it's equal to negative 1. So it's symmetric about the y-axis, which means that cosine of theta is the same thing as cosine of negative theta. So you plug in a negative angle, you get the exact same thing as if you plugged in the positive. Whereas for sine, remember, it was this. If you plug in a negative angle, you get negative as if you plugged in the positive angle. Okay. So that's the base function. But let's do an example. Let's do f of theta equals cosine of 2 theta plus pi over plus pi minus 1. Okay. Actually, let's just do plus pi. We don't need to make it super complicated. Okay. Now, one thing I want you to notice here. Notice we have 2 times pi, or 2 times theta plus pi. But if you go back up and look at this, notice that our b here is multiplying by this entire thing, not just pi. Whereas our 2 here is not. So when you see a problem like this, when you have some number multiplying by the inside, the first thing you have to do is factor out that number. You have to factor it out to get the true value of c. So basically, we're dividing both of these numbers by 2. So we'll get theta plus pi over 2. Good. So we're actually shifting our function to the left by pi over 2. What's the 2 going to do here? The one on the outside.
Causes problems.
Causes problems, yes. In terms of translations, what's that? Or transformations, what's that going to do? You need to look at the...
Make it shrink it.
Shrink it? How?
By 2.
Yeah.
It's greater than...
No, yeah, no, you're right. You're absolutely right. But vertically or horizontally?
Horizontally.
Horizontally. Good. Good job. All right. So nope, I did that wrong. Shrink by 2 horizontally. Okay, so we only have 2 transformations this time. So let's do that. I think for this one, and I've done this before, so that's the reason why I think this, but I think we need to make it every pi over 4 this time.
Every pi over 4?
Yeah, because we're shrinking it by 2, which means that we're kind of shrinking that in, so it's going to be skinnier. So to get the full detail, we need to probably take it every pi over 4 instead of every pi over 2. So let's say we have cosine of 2 times 0 plus pi pi over 2. So cosine of 2 times pi over 2, what does that give us?
1.
So 2 pi over 2, they'll cancel, so that's pi. So then we have cosine of pi, which is what?
-1.
-1, right. This time I'm going to circle these with a different color because I don't want to miss them. Okay? So then we'll go up pi over 4. Ah. Okay. So we have cosine of 2 times pi over 4 plus pi over 2. So what's pi over 4 plus pi over 2? What would that be?
Three pi over 4.
3 pi over 4, good, yeah. So we have 3 pi over 4, and then we're multiplying that by 2, which will give us what?
Square root 2 over 2.
Oh, no, just the angle. I'm still looking at just the angles. So the 2 will cancel there, so it'll give us 3 pi over 2. So cosine of 3 pi over 2 is what? It's the
0.
0, good, yeah. It's the x value at 270, so it's 0. Oh, whoops. Okay, we're almost out of time, so I'm going to try to do this quickly. So then pi over 2, that'll give us cosine of 2 times pi over 2 minus pi over 2. Well, that's just cosine of 0, right? Because that'll cancel. So cosine of 0 is 1, right. Okay. And then we'll do one last point. 3 pi over 4. So cosine of 2 times 3 pi over 4 minus pi over 4. Wait. No, pi over 2, excuse me. So what's that? It's 3 pi over 4 minus pi over 2. Let's break it down.
Pi.
So pi over 2 is the same as 2 pi over 4. So with that,
1/4 pi.
yeah, so pi over 4. And then we multiply that by 2 because of this. So that's just pi over 2. Okay. And then so what's cosine of pi over 2?
0.
0. Good. Okay. So we got all our points now. So at 0, it's -1. At pi over 4, it's 0. So that's halfway in between 0 and pi over 2. Pi over 2, it's 1. And at 3 pi over 4, it's 0 again. So that is going to look like this. That's all we found right there. Unfortunately. That's all we found right there. But if we keep on going, it's going to look like that, basically. And the same thing on the other side. So you can see that we shrank it, like an accordion almost, by a factor of 2. And we also shifted it left by 90 degrees, by pi over 2 as well. So we shifted this function, this green function, left by 90 degrees. Yeah. So, all right. That is our notes for today. I will post a homework